Good day. So, in this lecture we will be discussing about one very important component of worldwide communication, which is satellite communication. Communication through satellite has been going on for quite some time now. So, that way satellite communication is a fairly what should I say, mature technology. Although some improvements are taking place, etc. So, satellite communication is an important component of worldwide communication infrastructure, and not only that, we will also see how specifically MAC, which is media access control, is handled in satellite communication. This is important for, and we obviously we require some MAC over here, because the communication medium is the electromagnetic field around us, which is common to everybody. All right. So, we talk about satellite communication. A communication satellite can be looked upon as a big microwave repeater. Okay. You know what is a repeater? A repeater is something which repeats the signal. That means, it takes in the incoming signal, amplifies it, and then sends it back. So, it contains several transponders, they are called transponders, which listens to some portion of the spectrum. So, each transponder is listening to some portion of the spectrum. So, that several transponders together are listening to a wider band of the spectrum. It amplifies the incoming signal and broadcasts it in another frequency back to earth. So, satellites are of course sort of in this up there in the space. So, it takes the incoming signal, amplifies it, and broadcasts it back. It has to broadcast in a different frequency, so as to avoid interference with the incoming signals. So, this can relay signals over long distance. All right. So, this is one strength of satellite communication, because if you send it all the way up, and then when it is sending it down, if it does so at an angle, then it the signal can reach a very long distance. There are different kinds of satellites, and one of the most commonly known ones are the so called geostationary satellite. They remain above the equator at a height of 22,300 miles approximately, which is the geosynchronous orbit. Travel around the earth in exactly the time the earth takes to rotate. So, this is the example. So, we have what is an uplink station from where some signal is going, and then it is being listened to by the one particular transponder in the satellite. It amplifies that signal and sends it back to earth, where the downlink station another dish, which is sort of focused, or which is sort of facing the satellite or tracking the satellite. This receives the signal, and this receives the signal in a horn over here. So, this is just the reflector part. So, this reflects and it gets into the horn, and from the horn this signal is taken down, amplified, and then we can use it. So, earth stations communicate by signal satellite on the on an uplink. They are called earth stations or base stations on the ground. The satellite then repeats these signals on a downlink. The broadcast nature of the downlink makes it attractive for services such as distribution of television programming. I mean, we all know that many of our television channels, unless it is coming through some cable, it comes from some satellite. So, what is happening is that when satellite is beaming it back, it is the signal reaches a very wide geographical area, and all the receivers around can receive this signal and then amplify it and use it. So, it is very popular for such kind of applications like distribution of television programming. There are other applications, we will talk about them. So, these signals are used to transmit signals and data over long distances, like weather forecasting, television broadcast, internet communication, global positioning system. So, these are various applications of satellite, and space orbit allows more surface coverage. Now, there are some about the spectrum which is usually used by the satellite. they are sort of divided into some sections, and each of these bands have some name like C band, Ku band or Ku band or Ka band or Ka band. Okay. The C band it may have 4 downlinks and 6 uplinks. So, it is at a particular, so this is the C band is from 3.7 to 4.2 gigahertz. This particular part of the spectrum is reserved for the C band communication through satellite. So, 3.7 to 4.2 gigahertz for downlink and 5.925 to 6.425 gigahertz, this is for uplink. Okay. So, there is a 0.5 gigahertz bandwidth for downlink and another 0.5 gigahertz for uplink. Of course, since the uplink is at a higher frequency, so you can have more channels over there. So, capacity is low in the sense that the capacity is not very high by today's standard, especially I mean if you compare it with fiber. So, this is really low, but at the same time at one point of time when transoceanic fibers were not there, satellite was the chief medium of communication across continents. All right. So, capacity is low, but still it is useful, and terrestrial interference is a problem. So, interference is a problem in satellite, because if the weather is bad or if there are other kinds of extraneous sources of some electromagnetic noise etc., this interferes with the signal. So, this is always a problem, but still it has got a lot of strong points. So, that is why it is still an important component of communication these days. Next set of transponders come in the so called Ku band, Ku band. All right. So, we have seen about C band. The Ku band has a greater number of it can accommodate a greater number of transponders, 12 on the downlink and 14 on the uplink. Rain interference is a major problem here. So, Ku band is from 11.7 to 12.2 gigahertz and 14.0 to 14.5 gigahertz. And in this band rain is a problem, though it has higher capacity and is less crowded than the C band. C band is very crowded. By the way, if you look at people who has got dishes or sort of dish antenna for receiving satellite signal, I mean for ordinary users, I am not talking about the base stations. So, the ordinary users. So, the ones who use about say a 1 meter kind of antenna, they are possibly using the C band, whereas for the Ku band the antenna size is much smaller. It is a pizza shape at something like 18 to 20 inches. So, those are Ku band antennas. All right. So, they have a higher capacity etc. is there, but of course, and different parts of the spectrum, as I said, the rain is a problem here, terrestrial interference is a problem in C band. So, different parts of the electromagnetic spectrum are more susceptible to different types of interference and noise etc. So, here this is the rain is a problem, but it has higher capacity and is less crowded, this Ku band. And next we have the Ka band, so which is at an even higher frequency, Ka band, so 19 downlink or 29 uplink transponders. So, equipment needed to use the band is still somewhat expensive. It is from the 17.7 to 21.7 gigahertz. As you can see that is a lot of bandwidth, and 27.5 to 30.5. So, it is a greater bandwidth, but it is still not very widely used. Okay. Now, for satellite can be used for point to point transmission to transfer large volume of data, voice, data etc. communication, for video conference. So, satellite is not just for broadcast, satellite can be used for point to point communication. Okay. Broadcast of course is always there, and broadcast you or you may also look at it as point to multi point communication. So, point to point communication is supported, point to multi point communication is supported, and of course, standard broadcast is always supported. So, point to multi point transmission can be data communication, internet, video conference etc. So, they are their applications. and broadcast services such as television. So, these are the different types of uses we have, and the advantages are we can reach a large geographical area, we have a high bandwidth in some sense, cheaper over long distances, although I mean it is certainly cheaper than varying it up, but if you are just covering long distance through fiber optic cable, because of its inherent high capacity, the economics has changed. So, the fiber optic cable is coming out to be almost at least even in some cases, but even then in many situations satellite retains its advantage. Okay. And then it can transmit to places where cable cannot reach. Now, these are applications where satellite have an undoubted advantage over any other wired kind of system, all right, because I mean it may be a remote area, let us say, which is not very easily reachable, maybe road or other kind of communication is not well established. So, how do you take your cable over there, fiber or whatever, how do you take it? So, sometimes it is difficult if not impossible practically to take cables to such places, but satellite, since it is sitting high up in the sky, it can just it can cover just any area without any difficulty. So, this is a very strong point of satellite, and especially useful for technology displayed at deployed at multiple sites regardless of location, like mobile technology. Okay. So, when you want to be mobile, of course, nowadays mobile communication, the first thing people think about are the cellular phones, etc., which use the nearest base station, which is usually wired, but in some places where it cannot be wired, it may go through the the base station in its turn may be connected to the backbone through a satellite. That is one thing. And if you want 100% roaming all over the earth, wherever you go, then you may not have a base station around around the place where you are in, maybe in a remote area. So, in that case, but still some satellite or the other would be visible to you and you can communicate through satellite. So, mobility and reaching out to places which are difficult to reach otherwise, these are very strong points of satellite, and of course, standard communication through standard this thing is also there. Disadvantage of course is the high initial cost. You have to build the satellite is costly, and then to put it up in the space through some launch vehicle, that is also costly. But of course, I mean laying fibers all over also are costly. So, you have to work it out in some particular situations that which one comes out to be better. Susceptible to noise and interference, this of course we cannot do much at the physical level, because in the physical media is such that all kinds of noise are being generated all over the place and pouring into our shared this great shared medium. So, we cannot help it. So, we have to handle it in some other way at a higher layer, as we have already seen. Then there is a propagation delay. This is actually a significant disadvantage compared to terrestrial communication, because for many satellites, especially the geostationary satellites, and we will come back to this point later on, the geostationary satellites are thousands of miles above Earth. So, although I mean your electromagnetic signal is travelling at the speed of light, which is I mean very high, but even then to go all the way up to the satellite and then come all the way back down, that takes significant amount of time, and this significant amount of time has a lot of implications. It has implications on the Mach, and of course, it has other implications like delay and all these things, and maybe quality of service in some cases. So, this is an issue, this is a potential disadvantage. And security can also be an issue, because since this medium is open to everybody. So, whatever you are communicating, anybody else can listen on to it. So, if you are trying to send some very sensitive data etc. Through satellite and you do not want other people to listening to what you are sending, then you have to take some other measure like encryption etc. So, we will talk about encryption much later in the course. Now, there are different types of satellites and they have different types of orbits, circular or elliptical orbits. Okay. So, in this for the circular orbit, the circular with center at the earth center, okay, that is a circular orbit, elliptically with one foci at earth center, these are the possibilities. And then the plane of orbits, there are some equatorial orbits above earth's equator, okay. This is quite common. This is quite common, especially for geostationary satellite, this is necessary that they go around the equator. But then you could also put satellites which go on a circumpolar orbit, that means it passes the polar orbits pass over both the poles, and other orbits referred to as inclined orbits. And what about the altitude of the satellite, how far are they from the earth? As I mentioned earlier that this has significant implication in terms of the time it takes for the signal to travel. So, we have three different satellites are usually they are classed into three different classes: geostationary orbit satellites GEOs, medium earth orbit satellites MEOs, and low earth orbit LEOs. Out of all this, GEO is the most common one. So, GEO they go around the equator and high bandwidth. So, it gives some high bandwidth, but it also requires high power. This is an important point, and long latency. These are the important issues. You see, the point is that when you are trying to communicate with some satellite which is very far away, then your transmitter has to be strong enough so that the signal reaches the satellite, all right. And if the if the transmitter power has to be large, then you require a sort of a lot of power. I mean, in order to power this, it may be difficult to power it with a battery, let us say. So, if you are thinking of a very small footprint device like what you have in say cell phones etc. of that kind of size, the battery power may not be enough to reach a geostationary satellite. So, you are essential. So, the one of the points we were talking about as the mobility, that becomes difficult from this power angle. So, this is an important issue, and latency, of course, high latency. MEO is once again it has got a high bandwidth, medium kind of power and medium kind of latency naturally, and LEO which is about let us say 400 miles, this is a ballpark figure, it varies, low power and latency, but you require more number of satellites, they have small footprint, we will see why. And of course, we use a VSAT which is very small aperture. Now, when you talk about a VSAT, you are not actually referring to any satellite, you are referring to the ground equipment that you use, and VSATs are very small aperture this thing which private vans or private people can use it, they are small antenna. Okay. So, usually through this VSAT private people can communicate, but if they are using C band or Q band, they are that antenna, that either 1 meter or 18 inches and kind of antenna you require. But for the main base station of the satellite, usually a much larger antenna is put in place. So, first we talk about geostationary satellites. This is the most common type of satellite today. It is in a circular orbit. In kilometers we said, in miles it is about 22,000 odd, in kilometers it is 35,000 and odd kilometers above the earth in the equatorial plane. These satellites remain in the same position over the earth as it rotates. So, this is a, so if you see that as the earth is moving, the satellite is moving along with that, and so far as the some point on the earth is concerned, from some point it would appear that the satellite is sort of stationary over its head at all times. So, this is this is why this is so sacrosanct, this geostationary satellite and this distance of 35,785 kilometers. You can always calculate this distance, finding out about the centripetal force and the earth's gravitation, etc. You can put it in that equation and calculate that this is the exact distance at which, if you put a satellite with a particular angular velocity, which is the same angular velocity as that of the earth, what will happen is that you will get to the people directly under it will appear as if the satellite is stationary. So, this is the good thing about this geostationary satellite, and this is why this distance is so fixed. And on a particular point of this thing, the one which is being shown, maybe it is fixed at this particular point. So, that and of course, from such a long distance, if you send a beam which is which has got a reasonable solid angle over here, this will cover a large portion of the earth. As a matter of fact, it has been calculated that with 3 or 4 satellites you can cover the entire surface of the earth, but of course 3 or 4 satellites would not be sufficient to handle the bandwidth that we require these days. And there are, and the other thing is that since this distance is so fixed, there is only one band in space where these satellites can be parked. And the other point is that if 2 such satellites are very close to each other, their signals will start interfering with each other. So, there has to be a minimum distance between 2 geostationary satellites, which are both of them are parked and that geostationary orbit. And these parking slots, they are internationally they are decided, but this parking slot is quite crowded. Okay. Some nations, they may not have put a satellite, but they have reserved some parking slot, and that this parking slot is quite crowded today with so many geostationary satellites up there on the earth, up there in the space. So, they have huge coverage, as I mentioned, about a fourth of the earth, and have good tracking properties. That means you can track it very easily, but their signal weakens over great distance and the propagation delay can be large. So, you see the propagation delay we are talking about is of the order of 0.24 seconds. Okay. Usually we talk in terms of milliseconds, but here we are forced to talk in terms of seconds, which is not a very good thing. It can also be hard to get coverage at the polar regions, because the polar regions, because these geostationary satellites has to be over the equator. So, to get coverage at the polar regions is difficult, and the far northern and southern hemispheres. So, they provide, of course, in its footprint. Footprint means that area of earth which is covered by one particular transponder, let us say on one particular satellite. So, it covers all that area at the same time. So, that is called the footprint. Okay. So, it is provides now within its footprint it covers universal connectivity at from any particular point you can communicate with that satellite, and possible satellite parking slots are quite crowded. Wide beams are circular, while spot beams, which are more focused, they are elliptical and they are more focused. Apart from broadcasting, they may also be used with VSATs for point to point communication. We will come back to this point later on. So, they are at this kind of distance. This requires large transmitter power, making them large and expensive. There is considerable space delay, we have mentioned this, and large cell size, which sizes means smaller number of channels. Okay. This is one particular point, and we will come back to this point in greater detail when we discuss terrestrial wireless communication. But the point is that a satellite, think of this, that a satellite has some amount of bandwidth which is assigned to it, which it can handle. Now, within that bandwidth for communication, if you think that the elementary communication, let us say voice channels which require that DS0 kind of rate, meaning say about 64 kbps rate. Now, how many such 64 kbps channels can be handled in one particular transponder? Let us say it can handle say 800 such channels, alright. Now, if the beam is or its footprint of the satellite is very large, okay, then that means that it is covering a large number of people, but all these large number of peoples are constrained with those 800 channels, okay. You cannot increase it because that is not possible. So, a large cell size also necessarily means a smaller number of channel density, let us say, on Earth, okay. A typical satellite has 12 to 20 transponders, each with a 30 to 50 megahertz bandwidth. A 50 Mbps transponder can carry about 800 voice channels. FDM was used, that is frequency division multiplexing was used in early satellites. Nowadays TDM is also used. As a matter of fact, a mixture of TDM and FDM are also used. The cost of transmission is independent of this distance. This is another, I mean sometimes this is an advantageous point, which is that whether you suppose you are communicating via a communication satellite, whether you are communicating with somebody who is only say 10 kilometers away or with somebody who is 100 kilometers or 1000 kilometers away, the thing is the same. You have to go so much up and so much down. So, the cost is constant over the entire footprint, okay. That may be an advantage in some cases. The cost of transmitting to the other thing is that the cost of transmitting to one is the same as cost of broadcasting it. For some application, once again this may be useful, okay. So, this is a good broadcast medium. Security and privacy is a problem as mentioned earlier. So, encryption is essential. Mobility is easily achievable and setup time is not required. If the satellite is there in space, then there you do not require any setup time. If the satellite is not there, of course, I mean you have to send it there. So, that is this thing. And GPS is an interesting application, we will see this. Then we come to a middle earth orbit or orbit satellites. These are used for global wireless communication coverage, maintain orbit about 8,000 miles from Earth, okay. Now, I mean the moment you come out of the geostationary orbit, the satellite cannot remain stationary over somebody's head any longer, okay. Now, the satellite will necessarily move over your head. So, in a MEOs and LEOs, what will happen is that you will find that the satellite is coming over your head. I mean it is just as other stars and this thing they seem to move. So, satellite will move in the sky and it will be there for some time and then it will be out of your reach because it will go down below the horizon. So, that is what is going to happen with MEOs as well as LEOs. Now, how soon they will come back etc., that depends on how far they are and what is their speed etc., etc. So, it orbits Earth about every 2 to 12 hours depending on its on these parameters. So, more satellites are needed and some handoffs are required as the satellites orbit. Now, the point is what is this handoff we are talking about? Well, you are communicating through this satellite, but the satellite has come. So, you are communicating through the satellite to somebody else, but the satellite has moved away. So, now the communication link will break. So, in order that the communication link does not break, what will have to happen is that another satellite will have to come and take its place, and there have to be a handoff of communication from this satellite to this satellite before this satellite disappears altogether. So, that this communication between the two endpoints can continue. So, these handoffs are required as satellites orbit and transmit data rate at 9.6 kbps to 38.4 kbps. Transmission delay is less than 0.1 seconds. Okay. So, this is considerably more considerably less than the 240 milliseconds we had earlier. And taking it still further down is the low earth orbiting satellites, launched like a large flock of birds. Now, you require a lot of satellites, because these satellites I mean each satellite is visible to one particular point on earth only for a very short duration of time. So, in order to cover in order to give continuous coverage, you need a large number of satellites, and if you want to cover the entire earth, first of all these cell size or the footprints will also become smaller. So, in order to cover the entire earth, now you need a very large number of satellites. So, orbits at constant altitude of 400 to 1000 miles must travel very fast to avoid gravity forces, because if it cannot travel any slower, okay, because in that case it will fall down. So, low Earth orbit allows for transmission at 2.4 to 9.5 kbps, travels at 17,000 miles per hour, circles Earth approximately every 90 minutes. So, this is going around very fast, used for mobile voice, low and high speed data, internet access via mobile phones and PDAs and GPS, etc., etc. So, the low Earth orbiting satellites are what are used for the so called sat phones. You know, the satellite phones, well, it came up once and now it is sort of dwindling due to some reason which I will come to that later on. But now, since this is low Earth orbiting, the power that you require to reach that satellite is much less. So, now you can have a handheld device, something maybe a little bigger than your standard cell phone, but not very much bigger, you can still carry it in your hand, and with that now you can phone from anywhere on earth, because you are just communicating through the satellite. So, low Earth orbiting satellites are individually cheaper, they also give lower space delay. Now, the space delay is much less because you are that much nearer. However, a large number of satellites need to be deployed. As the satellite keep moving, ground stations which are communicating will have to switch from one satellite to another. This is what I was talking about. So, once again quick handoffs will be required. One of the examples which are there was the Iridium set of satellites. There were 66 satellites which offered mobile telephony, paging and data communication. Unfortunately, it was bankrupted by 1999. What happened was that it gave sat phone services, but then it was very costly, all right, and by that time other kinds of technology, that is especially this fiber technology and the terrestrial wireless technology developed to such an extent that most of the major part of the market was captured by those which were giving the same service, maybe to the end user it looks like the same service at a much cheaper rate. So, this the money which you had to charge because of these 66 satellites which you had sent. By the way, you remember that if from the geostationary satellite 3 or 4 satellites are enough to cover the entire earth. Here we require 66 of them, okay, all of them moving very fast, and you have to have this complicated handoff from satellite to satellite. All that is required just to make it low enough so that you can communicate it from a handheld device, etc. So, that was there, but then this could not be supported in the market. Okay, you have very few people going to such remote places where there cannot be any infrastructure, etc. So, that portion of the market is naturally very small. For the overwhelming majority of the users, they would have some base station for some terrestrial wireless nearby. So, that is why this price became very uncompetitive, and there was some effort to revive this company, sell it to some others, etc., etc., but finally it did not work out and it has become bankrupt. And because of this reason, another ambitious project called Teledesic in the LEO, which includes 288 LEO satellites to provide low cost high speed internet access, networking and teleconferencing across the globe. This is also going slow, or it may be sort of it may not come up at all actually. Now, here as I mentioned, the space delay is lower and becomes comparable to terrestrial lines in the L band. It is possible to communicate with it using battery powered handheld devices. However, cell sizes are still too large compared to terrestrial cells. Iridium system had 66, as I said. So, each satellite was to have 48 spot beams, giving a total of so many 1600 cells, each with 174 channels, but 174 channels or total of 100,000 183,000 channels are not that many globally, because terrestrial service providers routinely give millions of channels over the area. So, finally, the cost turned out to be too high and the project went bankrupt. Then we talk about VSAT, which is small terminals with about 1 meter antenna and 1 watt power, 1 watt transmitter power, that is. Often the downlink capacity is more than the uplink speed, is for point to point communication, usually goes through a hub, that is 2 hops, which means that if 2 persons want to communicate, his communication will go from here to the satellite, from the satellite to a central hub, which will have a very big antenna and it can handle all these different. So, this will handle the MAC part of it, we are not going into the details of this, but anyway this will go to the hub, and from the hub again it will go to the satellite and then go to the point B, say A was the sender and B was the receiver. So, from A to B. So, it goes in 2 hops. So, the space delay is doubled, okay, because we are going in 2 hops. Sometimes with the help of a satellite modem kind of thing, you can go in 1 hop sometimes. So, those channels are more costly, otherwise the usual one is that 2 hops. So, you get considerable delay now of the order of a half a second kind of delay for this communication between A and B. But then there is no setup time. So, you can set it up very quickly any way you like. So, various combinations of TDM, TDMA, FDM and FDMA are used for handling the MAC, and this is all controlled by that central hub. So, that is how it is done. One application, as I mentioned, one important application was the GPS satellite constellation. This is a global positioning system in the. So, this is operated by US Air Force. Okay. Another GPS system is on the drawing board. So, it will be deployed now by some other consortium. So, there are 28 satellites in this, and it has got 6 orbital planes at a height of about 20,200 kilometers. So, once again since this is not the geostationary orbit, so they sort of keep on moving and position. So, a minimum of 5 satellites are visible at all times. Okay. So, with this what you can do is that you can locate any position. So, on the ground, if you have a GPS terminal somewhere, now it may be a very common application of GPS is to put that antenna on a car. So, the car can be tracked anywhere on earth. Okay, that is where it is, that is exactly where it is. Okay. And the receiver measures the distance to the satellite. So, what happens when you do that? So, for GPS we do a trilateration, that means if there are a number of satellites which are visible to any of these. So, here the picture shows a ship, plane and a car. For all of them they hold, let us say for the car. Now, this is measuring its distance from a number of satellites, and since how the satellites move at what point of time, etc., those are known from these 3 different readings, 3 different distance measurements. If they are measured quite precisely and accurately, then you can get the accurate position of the car. Now, what is the good thing about having an accurate position of the car? Well, there are so many different applications which are possible. For example, there may be a central database which knows that from that point, say that car is presumably, let us say, on a highway. So, if the central database, if you also give information about where you want to go, then it can tell you that okay, this is the path you take. Maybe there are alternative paths and one of them is crowded. So, do not take that, take this one. So, and that kind of application is already there in many places like Europe and all. So, you can get very precise information about where you are, which road you should take and which series of roads you should take, which series of turns you should take to reach your final destination. So, that is just one application of GPS, there are all kinds of other applications. Then automatic vehicle location. Okay. So, maybe this shows a mobile GPS unit. So, this mobile unit is on a truck. So, these GPS satellites are there. So, you can give fast dispatch, customer service, safety, security, digital messaging, dynamic route optimization. For example, say some company delivers a lot of goods to a lot of maybe warehouses and things like that. So, it has maybe shipped something, and now the customer wants to know that I ordered for this, where is it? Okay. You can immediately know where it is, because you know that in which truck you have put his goods and where it is exactly. Okay. So, you can so for courier service and that kind of service you can give very good and a different level of service through this GPS. So, in conclusion we can say that satellite communication will continue to serve where broadcasting is essential or where terrain is hostile or very sparsely populated. It also has a niche where right of way is difficult or where rapid deployment is extremely critical. Okay. Let us say in a battlefield kind of situation or some situation where you want to rapidly set up some communication network. So, if you have a satellite up in the sky already, you can take that transponder, maybe there is a disaster somewhere, so you want to quickly set up disaster recovery, relief, etc., etc. So, you can use this satellite, because satellite communication will still go on, whatever may have happened, there may be a flood, everything may be flooded, but the satellite communication will still go on if you move in with your mobile units. So, where rapid deployment is extremely critical. In other areas, a combination of terrestrial radio links with fiber is likely to hold the advantage. Now, we come to one interesting part of this satellite communication, that how this MAC for satellite communication, how is the media access control handled. This is another class of media access control techniques which we just mentioned earlier. So, this is the first example that we see, namely random access protocols. We mentioned random access protocols earlier, just as we talked about token based protocols, etc. We also talked about random access protocols. So, this is the first example of a random access protocol. Now, random access protocol is actually very simple. When node has packet to send, transmit at full channel data rate. Okay. So, just do not bother whether somebody else is transmitting or not transmitting, or wants to transmit or is going to transmit right away. You just do not bother about anything. You just try to put in whatever you want to transmit onto the channel. Now, what will happen if you are lucky, since you are doing a random thing without any knowledge or consideration about what other people are doing, you may be lucky and your transmission may go through. Okay. So, there is no a priori coordination amongst the nodes. So, but your transmission may still go through just by chance, all right. Otherwise, what will happen is that two or more stations may try to start, they may want to communicate at the same time or very nearly the same time. So, what is going to happen is that the packet or the frame sent by one station A and the frame sent by station B, they are going to go and collide. Okay. And what will happen is that, so this is a collision, and what will happen is that both the frames will be lost, it will become garbled. But since you are talking about a medium which is shared by everybody, these two transmitting stations A and B, they would also be able to listen to this and find out that okay, both of their communications they are garbled. Okay. And if they find that both are garbled, what they will do is that they will say that no, we have to retransmit. Okay. And then what they do is that they sort of back up for a random amount of time. Now, that is very important. Once again, this second randomness is also very important, this backing up for a random amount of time, because if the protocol says no, both of them back up for a fixed amount of time, then after the lapse of that fixed amount of time, both of them will start communicating again and both of them will collide again, and again it will get garbled. So, it is important that that they back up for a random amount of time, and hopefully the random number generated by one station and the random number generated by the other station, they are going to be two different numbers. So, now they are going to try communicating at two different points of time where they will not collide. Okay. But they may, at that point they may collide with other stations, that is a different issue. So, this is in short the random access protocol. So, if two or more transmitting nodes start transmitting at the same time, what we have is we have a collision. Random access MAC protocol specifies how to detect collisions, how do you know that your thing has collided, and how to recover from collisions, for example via delayed retransmission. So, this is the two parts of any random access MAC protocol. This satellite protocol, which is called ALOHA or slotted ALOHA, are the simplest kind of random access protocol. We will see other examples like CSMA, CSMA-CD, CSMA-CA, etc., that we will see them later on. So, these are the examples of random access MAC protocols. ALOHA, which was the original grandfather of all these protocols, then came slotted ALOHA, and then all these CSMA, CSMA-CD, CSMA-CA, etc. Now, the ALOHA protocol was originally developed for packet radio in 1970s, approach applicable to any system with uncoordinated users competing for a shared channel. User transmits frames whenever ready, as I said, no carrier sensing. What does it mean? Carrier sensing means you do not try to find out whether or not somebody is already communicating. Okay. Now, that may sound a little strange at first, because if you could find out that somebody is already communicating, then by trying to transmit at that point of time, you are not only not only that you are guaranteed to fail, because your own thing will get garbled, and somebody else's frame will also get garbled, and you will have a more crowded media later on. But for satellites there is a problem. Okay. You cannot always do this carrier sensing, the main reason being the space delay, all right, because whatever you are listening now, okay, if you think about it. So, since we have a 240 millisecond space delay, so whatever you are listening to now was actually transmitted 240 milliseconds earlier. So, if you find that the channel is sort of quiet now, there is no guarantee that after 240 milliseconds also it will also remain quiet from other positions. Okay. So, that is why it is difficult to do carrier sensing in the case of a satellite. So, that is why this latency, space delay, has a very significant impact on how we handle the MAC. So, here since we cannot do it, we do not do it. Okay. We can do it of course, but it does not make too much sense, because 240 milliseconds is a lot of time in which maybe a number of frames may be sent. So, we do not do it, we do not do any carrier sensing, we simply send whenever we have to send something, and then later on listen to the medium to find out whether or not there has been a collision. So, this is the pure ALOHA protocol. Users transmit whenever they have data. If there is collision within a time frame dictated by the space delay, it backs off for a random amount of time and sends it again. If the first bit of a new frame collides with the last bit of a frame just finishing, both are taken to be garbled. Okay. So, there is no such thing that a frame has gone through with a 95%. Okay. Either the frame has gone through entirely, or even if only one bit has collided, even then both the frames are taken to be garbled and lost. So, collision detection by listening to broadcast channel or by absence of acknowledgement. If collision occurs, each user waits random length of time, as already mentioned. Various collision resolution algorithms are available. Station does not transmit new frame until old frame has been successfully transmitted. So, the station is stuck with that frame until it can send it. In slotted ALOHA, which has a somewhat better performance, what is done is that all frames are of the same size. Time is divided into equal size slots, which is that each slot is a time to transmit one frame with some this thing. Anyway, so now if the transmitters and receivers are synchronized, they try to send frames only at the beginning of a slot. So, nodes start to transmit frames only at the beginning of slots. Nodes are synchronized. If two or more nodes can still try to transmit in a in slot, all nodes detect collision. I mean, you may still collide even if after making the slots. For example, suppose within the span of the 5th slot, 3 different stations have gotten ready to transmit something. Now, what will happen is that at the beginning of the 6th slot all 3 will start communicating and all 3 will go and collide. So, when node obtains fresh frame, it transmits the next slot. So, as soon as it gets a frame to send, it sends it in the next slot. No collision, node can send new frame in the next slot. If collision, node retransmits frame in each subsequent slot with probability p until success. So, this is a picture of a slotted ALOHA. So, this is there is a collision over here, 3 nodes, nodes 1, 2 and 3, all 3 of them wanted to transmit. So, they did start transmitting and then they collided. Then all of them backed off. It may so happen that the second slot went empty because none of them want this thing. Then again in the third slot what happened was that 1 and 2 node number 3 had backed off randomly for a long period of time, but node 1 and 2 may have decided on the same number over here. So, 1 or 2 collide again. What might happen is that, I mean this is just by way of an example, maybe in the 4th slot 2 has tried again and it has been successful. So, there is a success over there. Then next slot is empty. In the next slot node 1 and node 3 they try and then they collide again. Then maybe the next slot is empty, maybe in the next slot node 1 succeeds, maybe in the next slot node 3 succeeds, and so after 1, 2, 3, 4, 5, 6, 7, 8, 9 slots, now the 3 have been able to communicate these 3 frames. Okay. So, you see because of this collision this takes its toll on the efficiency, but that is the way it is, you cannot help it. So, slotted ALOHA pros is single active node can continuously transmit at full rate of channel. That means, if nobody else wants to transmit, one active node can go on transmitting. Okay. Highly decentralized, only slots in nodes need to be in sync. So, that may be taken care of from the hub or this thing through the satellite etc., and it is a very simple kind of protocol. Cons is of course collisions, wasting slots, idle slots, low efficiency, that is always the cons. Now, what is the efficiency like? Efficiency is the long run fraction of successful slots when there is many nodes, each with many frames to send. Suppose n nodes with many frames to send, each transmit in slot with a probability p. So, probability that first node has success in a slot is equal to p into 1 minus p to the power n minus 1. So, it is the probability p that that particular node sends, and it is the probability 1 minus p that all the other n minus 1 do not send. So, only then you will have a success, and probability that any node has a success is n p into 1 minus p to the power n minus 1. So, for maximum efficiency with n nodes, we have to find a p star that maximizes n p into 1 minus p to the power n minus 1. So, their value will depend on n for large n, and then I am not going into the details of the calculation. For many nodes, take the limit of n p star into 1 minus p star to the power n minus 1 as n goes to infinity, and this gives a value of 1 by e, which is 0.37. So, this is the efficiency, 37% is the maximum theoretical efficiency that you can achieve in slotted ALOHA. So, at best channel used for useful transmission 37% of the time, which may not look like a very high figure, but then you are absolutely uncoordinated, but if you have low load then that may be alright. For pure or unslotted ALOHA, its unslotted ALOHA is simpler, no synchronization. When frame first arrives, transmit immediately. So, collision probability actually increases. Frame sent at T0 collides with other frames sent in T0 minus 1, assuming that each frame takes 1 unit of time to send, up to T0 plus 1. So, there is a big interval from T0 minus 1 to T0 plus 1 where things may collide. Remember, even the first and the last bit collide, still there is a collision. So, this will overlap. So, this frame will overlap maybe with this frame will also overlap with this frame, and now there is no question of any slot. So, anybody can start transmitting at any point of time. What will the efficiency be like? P of success by a given node is equal to P that the node transmits, probability that the node transmits, multiplied by the probability no other node transmits in T0 minus 1 to T0, multiplied with P probability that no other node transmits in T0 to T0 plus 1. So, this is P into 1 minus P to the power n minus 1 into 1 minus P to the power n minus 1 once again both of them. So, P into 1 minus P to the power 2n minus 1, 2 into n minus 1. So, choosing optimum P and then letting n tend to infinity gives us a efficiency of 1 by 2e or about 18%. So, this is a rather low efficiency for transmission, but then for with unslotted pure ALOHA, that is the efficiency that you get. Thank you. Good day. Today we will talk about Ethernet. This is possibly the most ubiquitous LAN technology today. As a matter of fact, when computer network developed, there were a number of competing LAN technologies, but today Ethernet has come to dominate LAN almost totally, excepting for the newly emerging wireless part, which we will discuss later. This Ethernet, as a matter of fact, not only LAN, nowadays people are talking about Ethernet in the MAN, that is metropolitan area network also. So, Ethernet, as you understand, is very important. So, we will talk about Ethernet. It is a dominantly a data link layer technology, and the multiple access scheme of Ethernet is CSMA-CD. Now, this minimum time is which may vary from a system to system, that means a network to network. So, this is how it is calculated, and first of all let us see how the minimum time would come. So, suppose this is the shared bus, we put two nodes at the two extreme ends. Suppose now packet starts at over here at time t equal to 0, packet is almost reached B at time t minus epsilon, at which point of time, so suppose this transmission time, propagation time of the, not transmission time, the propagation time of the packet from one end to the other, suppose that is tau. So, at tau minus epsilon it has almost reached B. At that point of time B starts transmitting, because B all this while has been finding that the bus have been very quiet, there is no signal on it. So, B can start transmitting. So, B starts and there is a collision, and this collision is at this end of the medium. So, now the collision bus starts travelling back, the jam signal and all that. So, that starts travelling back. So, it again takes a time almost tau to reach A. So, the total time is 2 tau noise. So, collision detection can take as long as 2 tau.